The integration process and the indefinite integral. The integration process. The field of mathematics is teamed with operations and inverse operations, processes and inverse processes. Addition and subtraction are two inverse operations, so with multiplication and division. Exponential function and logarithmic functions are inverse functions of each other, so with sine and arcsine, tangent and arctangent, secant and arcsecant, etc., etc. Differentiation and integration, on the other hand, are two inverse operations in the field of calculus. The integration process. We define the integration process as the inverse operation of differentiation. It is also referred to as anti-differentiation. The process involves finding a function f of x such that its differential f of x dx is given. The relationship between the lowercase and the uppercase is denoted by the small d to denote differentiation. In the context of integral calculus, the relationship can be written as the integral of fx dx equal to f of x plus c. The elongated s is the symbol of integration. This expression represents the relation between f and f by the symbol d representing differentiation. This one involves the relation between f and f in the context of integral calculus using the elongated s. This is called the indefinite integral because of the presence of the arbitrary constant c, or the constant of integration. So later on, we will see the relevance of affixing c in the integral of fx dx. This is called the indefinite integral and is read as the integral of f of x dx is equal to f of x plus c. Say we want to find the integral of 3x squared dx. A solution to this integral is x cubed, because clearly if we are to get the differential of x cubed, we will be getting 3x squared. Another solution is x cubed plus 4. Taking the differential of x cubed plus 4, we will be getting the same differential 3x squared dx. Still another is x cubed minus pi. If we are to take the differential of x cubed minus pi, negative pi being a constant will be 0, thus we'll get 3x squared dx. Still another solution is x cubed plus 1 half. The same thing, if we are to get the differential of x cubed plus 1 half, it will give us 3x squared dx. So notice that all these solutions differ only in the constant. Hence, we may write the general solution as the integral of 3x squared dx equal to x cubed plus c being the constant of integration. So this gives meaning to the name indefinite integral. It is indefinite in the sense that it involves an arbitrary constant c. We now discuss the fundamental integration formulas. The integral of dx is equal to x plus c. Getting the differential of x plus c will give us dx. Next, the constant multiple k of f of x dx. The integral of k fx dx is equal to k times the integral of f of x dx. So the role of the constant k is merely a multiplier that can be written before the integral. Next, the integral of the sum or difference of f of x, g of x dx is equal to the sum or difference of their respective integrals. The next one is called the power formula. It says that the integral of x raised to n dx is x raised to n plus 1 all over n plus 1 plus c n not equal to negative 1. So n could be any real number except negative 1, because we know what will happen if n is equal to negative 1. We will be getting 0 in the denominator, and we are not allowed to divide by 0. So the power formula involving x raised to some power n is for any n except negative 1. Let us now work on the following example. The integral of dy is simply y plus c. Formula 1 says that the integral of dx is equal to x. So the integral of the differential of y is equal to y plus c. Next, the integral of dt is equal to t plus c. The integral of dz is equal to z plus c. The integral of 4dx. 4 is a constant, so we can write it before the integral sign, dx. And we know that the integral of dx is x, plus the constant of integration, c. Next, we integrate x raised to 5 dx. This falls under the power formula. So we add 1 to 5. It becomes x raised to 6 all over 6 plus c. The integral of t to the negative 2 dt. Again, using the power formula, we have t raised to negative 2 plus 1 all over negative 2 plus 1 is negative 1 plus c. So that is equivalent to t raised to negative 1 over negative 1 plus c, and final answer can be written as negative 1 all over t plus c. Next, the integral of x minus 5x raised to 4 dx. That is equal to, since it involves a difference, we can write this as the integral of x dx minus the integral of 5x raised to 4 dx. So evaluating these two separately, x dx, the power of x here is 1, so it becomes x squared all over 2, minus 5x raised to 4. 5 is merely a multiplier. We integrate x raised to 4 dx, which is x raised to 5 all over 5 plus c. So we can cancel the 5 here. Final answer is 1/2 x squared minus x raised to 5 plus c. Next, the integral of y times the quantity 5 minus 3y dy. So first, we distribute the y. Y times 5 is 5y minus y times negative, or y times 3y is 3y squared quantity dy. Again, this involves a difference, so we evaluate the integral term by term. The integral of 5y dy is 5y raised to 1 plus 1, 1 being the power of y. So 5y squared all over 2 minus 3y squared dy. So we add 1 to 2, it becomes y cubed all over 3. And since we have a 3 here, 3 will cancel. Thus, we'll get y cubed plus c. Finally, we have the integral of the quantity square root of x minus 2 squared dx. So what we do here is we expand, right? The square root of x minus 2 quantity squared will be equal to square root of x squared. Square root of x squared. Twice the product of square root of x and negative 2. So that is negative 4x to the 1/2, or square root of x. And then negative 2 squared becomes positive 4 quantity dy. Or rather dx. That should be dx. Alright. So square root of x squared is x. So the integral of x dx is x squared all over 2 minus 4. This one. Huh? We evaluate this one, x to the 1/2. So it becomes 4x raised to 1/2 plus 1 is 3/2 all over 3/2 plus the integral of 4 dx is of course 4x plus the constant c. So our final answer is 1/2 x squared. 4 over 3/2, the 2 goes up, multiplied to 4, that will be 8/3 x to the 3/2 plus 4x plus the constant c. Next, we integrate c squared times 4 minus 3 over c raised to 4 dz. So distributing c squared, we have 4c squared minus 3. C squared over c to the 4th is c to the negative 2 quantity dz. Apply the power formula to 4c squared. That will be 4z cubed all over 3 minus 3z to the negative 2 plus 1 is negative 1 over negative 1 plus c equal to 4/3 c cubed. Negative over negative is positive 3. Z to the negative 1 is equivalent to 1 all over z plus the constant c. Next, the integral of 2 minus x quantity cubed dx. For this one, we expand 2 minus x quantity cubed. That will be 2 cubed or 8 minus 3 times 2 squared. So that will be 12x. Then plus 3 times 2, that will be 6x squared minus x cubed quantity dx. So what we do here is we multiply 2 minus x to itself twice. No? So 2 minus x cubed. This will be the expanded form. Okay, so we integrate term by term. 8 dx will be equal to 8x minus 12x dx is 12x squared all over 2 plus 6x squared is 6x cubed over 3 minus x cubed dx or x to the fourth over 4 plus c, which is equal to 8x minus 12 over 2 is 6x squared plus 6 over 3 is 2x cubed minus 1/4 x raised to 4 plus c. Say we are to evaluate the integral of the quantity 2x plus 5 raised to the power of 10. At this point, we only have the power formula x to the n dx. We do not have the formula for a function raised to some power n. So what we can do here is expand 2x plus 5 raised to 10 and it will generate 11 terms. It's even harder if the exponent is greater than 10. So it leads us to the next fundamental formula called the generalized power formula, wherein x is replaced by a function u. Take note that in the formula, u to the n is accompanied by its differential du. So before we can apply the formula, we have to see to it that the correct differential of du appears with u to the n. The derivation of the generalized power formula is not that difficult. We recall that the differential of u to the n is equal to nu to the n minus 1 du. In terms of integral, we write the integral of nu to the n minus 1 du equal to u to the n. And since n is a non-zero constant, we can divide both sides and we write the integral of u to the n minus 1 du equal to 1 over n u to the n. Now, we let n be equal to n plus 1. So all occurrences of n is replaced by n plus 1. So we write the integral of u to the n plus 1 minus 1 du equal to u to the n plus 1 over n plus 1. And u to the n plus 1 minus 1 is of course u to the n du equal to u to the n plus 1 over n plus 1 plus the constant c. Thus we have the generalized power formula. Again, before we can apply the generalized power formula, we see to it that we have the correct du accompanying u to the n. Now that we have the generalized power formula, let us apply it in evaluating the integral of 2x plus 5 raised to the power of 10. Clearly, from our integrand, our u is 2x plus 5. Our n is equal to 10. So we have to check the differential. Take the differential of u equal to 2x plus 5. The differential of u is du, and the differential of 2x plus 5 is 2 dx. So we need 2 dx to complete our du. So we write the integral of 2x plus 5 raised to the power of 10 dx but it says that our du should be 2dx. So there is a missing term here, or a missing constant 2. So we affix 2 to complete our du, but then it will change our integrand. So in order not to change the integrand, we can multiply it by 1/2. After all, 2 over 2 is equal to 1. Purposely, we are introducing 2 inside the integral in order to complete our du. So now, we can write this as 1/2 integral of u raised to 10 du, and applying the power formula, u to the 10 becomes u to the 11th power. So u raised to 11 over 11 plus c, or 1 over 22. And our u is 2x plus 5 raised to 11 plus c. Alright? Now, instead of rewriting our integrand in terms of u, from here, we can simply write 1/2. And since we know that this is already u raised to 10, we can write here u raised to 11 all over 11, or 2x plus 5 raised to 11 all over 11 plus c, and it will lead us to the same final answer of 1 over 22 times 2x plus 5 raised to 11. Let us try the next one. We evaluate the integral of x times the quantity 5x squared plus 3 quantity raised to 8 dx. So let me rewrite this as the integral of 5x squared plus 3 quantity raised to 8x dx. So from the integrand, it already suggests on what should be our u. U is 5x squared plus 3 and n equal to 8. So just like what we did earlier, we get the differential. Du is equal to 5x squared. The differential should be 5 times 2x, or 10x plus 0 dx. We already have x dx in our integrand. It only lacks the constant 10. So let us complete our du. 5x squared plus 3 raised to 8, 10x dx. We pre-multiply the integral by 1 over 10. And see that we have here u to the 8 du. And the integral of that will be u raised to 9, or 5x squared plus 3 raised to 9 all over 9 plus c, or 1 over 90 quantity 5x squared plus 3 raised to 9 plus c. Let us take on the next one, the integral of the quantity 4 plus sine x raised to 4 cosine of x. So it is clear in our integrand that our u is 4 plus sine of x, and our n is 4. The differential of 4 plus sine x is 0 plus cosine of x dx. So see that the required du cosine x dx appears in our integral. So we can immediately apply the power formula. This is u raised to 4 du. And that equals u raised to 5 all over 5 plus c. or 1/5 4 plus sine x raised to 5 plus c. Observe that our integrand involves trigonometric functions, but we did not apply any of the trigonometric formulas for integrals. So it's important that we know how to apply an integration formula involving the function u. So in this case, we applied the generalized power formula. So it doesn't necessarily follow that if your integrand is exponential or logarithmic, you will be using an exponential or a logarithmic formula. Next, we evaluate the integral of x squared dx all over 5 minus x cubed quantity squared. Let me rewrite this as the integral of 5 minus x cubed raised to negative 2x squared dx. Let u be equal to 5 minus x cubed. Our du here will be negative 3x squared dx. The differential of 5 is 0. The differential of x cubed is 3x squared dx. Alright? So, our du is negative 3x squared. We only have x squared dx. It lacks negative 3. It lacks negative 3. Let us introduce negative 3 inside. And then multiply it by negative 1/3. So, we have here u raised to negative 2. And the entire thing here is your du. So apply the power formula or the generalized power formula. We write negative 1/3 u to the negative 2 plus 1 is negative 1 over negative 1 plus c. Negative 1/3 and negative 1 is positive 1/3 or 1 over 3 u plus c. But my u is 5 minus x cubed plus c. Alright, again, from this part, you can write your answer as negative 1/3 5 minus x cubed raised to negative 2 plus 1 or negative 1 over negative 1 plus c, and you finalize your answer and it will appear in the form 1 over 3 5 minus x cubed plus c. That agrees with our previous answer. Next, let us evaluate the integral of the square root of 2 minus 1 over x times 1 over x squared dx. We may rewrite our integral as 2 minus 1 over x raised to 1/2 1 over x squared dx. Let u be equal to 2 minus 1 over x. Your n is 1/2. So we take the differential of 2 minus 1 over x. Negative 1 over x is x to the negative 1. And its differential is negative 1 x to the negative 2 dx. Or x to the negative 2 dx, or 1 over x squared dx. And that is exactly what we have in our integral. So here is our u raised to 1/2 together with du. So our answer here will be u raised to 1/2 plus 1 or 3/2, or 2 minus 1 over x raised to 3 halves all over 3 halves. Okay? Plus the constant c. So that is already our final answer. Next, the integral of e to the 3x times the square root of 1 plus 2e to the 3x dx. Again, let me rewrite this as 1 plus 2e raised to 3x raised to 1 half e to the 3x dx. So at this point, it's very clear that our u is 1 plus 2e to the 3x. The differential is 2 times 3e to the 3x dx, or 6e to the 3x dx. Our n is 1 half. 6e to the 3x dx is our complete du. We go back to our integral, and the only thing we have involving the differential is e to the 3x dx. It lacks the number 6. So we should write 6 and multiply it by 1 over 6. So that will be 1 over 6. Again, 1 plus 2e to the 3x raised to 1 half becomes 1 plus 2e to the 3x raised to 3 halves all over 3 halves plus c. Or 1 over 6 over 3 halves is 2 over 18, or that will be 1 over 9. Alright? And then 1 plus 2e to the 3x raised to 3 halves plus c. The integral of dx all over x times ln x minus 3 raised to 4. Let me write this as ln x minus 3 raised to negative 4, 1 over x dx. My u is ln x minus 3, n is negative 4, du is equal to, the differential of ln x is 1 over x dx minus the differential of 3, which is 0. So the required du is dx over x. What we have is dx over x. So the answer is outright. That will be ln x minus 3 raised to 4, negative 4 plus 1. That would be negative 3. Negative 4 plus 1 is negative 3 all over negative 3 plus c. Or negative 1 over 3 ln x minus 3 cubed plus c. You can now try working on the following exercises. I hope you have learned something about the fundamental integration formulas, specifically about the power and the generalized power formulas. Thank you for listening.